Good afternoon. My name is Jaco Skutte, for those people who forgot me. I'll be taking over today and Wednesday's lecture for Dr. Hafka. There won't be any homework this week either, so you guys don't have to worry about that. Today's lecture is about using multiple global optimizations to solve difficult problems, and this is done using the PSO that I covered last time. And this is also a lecture, well, this was also presented at the SDM last year. I'll give the paper on the website too. I'll start off by giving some background and motivation, and then I'll outline the multi-run methodology and give some numerical results that we found using this approach, and I'll finish off with some conclusions. Okay, so all global optimizers can have difficulty when they try to solve very large scale problems. By large scale, it is meant very high dimensionality, very large design space, and sometimes you also see for the figure on this graph, you can see that there are a lot of local optima, and only the center one is the global optimum. So you can have these type of problems where there's a lot of noise present or a lot of local minima present, and that makes it very hard for a global optimizer to find it, especially in higher dimensions. So stochastic population-based methods like the PSO or genetic algorithms, you can try to improve the chance of finding the global optimum by allowing more fitness evaluations. You run the algorithm for a longer time, or you can increase the population size. So if you increase the population size, you sample the design space a lot more densely. So your chances of finding the global optimum improve. And you can also try to fine-tune algorithm parameters. So you can work around with, on a GA, you can work around with mutation rates or the niching parameters. On the PSO, you can work with the C1 and the C2 constants. So you can try to fine-tune the algorithm parameters. All three of these options require more fitness evaluations, and they don't always guarantee that you're going to improve your chances of finding the global optimum. So if you have only a limited time on the computer or a limited number of function evaluations, you can only perform that many FEM analysis on your problem, or whatever your constraint is. We can switch to a strategy that was first proposed by Lariche and Dr. Hafka in '93, and the paper they presented this idea in was using GAs to find the optimum ply arrangement on a composite. And this is a very difficult problem. It's a high-dimensional problem that has a lot of local minima. So they said, well, why don't you run a GA more than once on a problem, and by running it more than once, you improve your chances of finding the global optima. Instead of going those three other options of increasing population, fine-tuning, and allowing longer optimization runs, you just use a limited optimization, but you repeat it with different starting points. And these optimizations have to be independent. So you either have to make sure that you use a random number seed for the GA or the PSO, or you start with a different population. You initialize your population with a different distribution. And why we took to this idea was we were motivated by the PSO's convergence behavior. So if I show you this slide is about this is a 12 problems that were optimized using the PSO, and this is the Dixon-Sejo test set. It's just a common test set they use to quantify the performance of global algorithms. And as you can see, the lines indicate the probability of converging to the global optimum at a certain amount of fitness evaluations. So some of the problems, you see that the probability of finding the global optimum goes up really quick, coupled to the amount of fitness evaluations. So after 10,000 fitness evaluations, most of the problems, these group of problems, have converged. But for some of the more difficult high dimensional problems with widely spaced local minima, you see that the probability of finding the global optimum don't get much higher than 0.75. So then it starts leveling off. So no matter how many fitness evaluations you will allow for these more difficult problems, you won't ever have a very good chance of finding the global optimum. And just to give you the background how this graph was obtained, we ran 1,000 optimizations for each problem, and then you decide on a convergence criteria, and then you monitor how many of those 1,000 optimizations have reached this convergence criteria by the amount of function evaluations. Does anybody have any questions on that? Is that clear? Because the whole rest of the lecture sort of hinges around that. So, like I said, very large number of optimizations are performed, and the convergence ratio, CR, is calculated by the number of converged optimizations out of the total number of optimizations, which is 1,000 in this case. And the three problems that we're going to discuss in this lecture is the Gruyang, Shekl, and Hartman problems. For those three, the convergence tolerance in the fitness was 0.1 and 0.001 for the second two. So the assumption that we make is that 1,000 optimizations is enough by the law of large numbers to quantify the convergence ratio. We assume the convergence ratio is the same as the convergence probability. So first we investigated what happens if you try one of those three measures that I discussed, and this one is both increasing the number of particles in the PSO. So you can see for 10 particles, the probability of convergence levels off at about 0.65, and this improves when you use 20. You get about 0.8 or 80%, and 50 particles 95%, and using 100 particles you get almost 100% probability of convergence. But you can also see from this graph that there's a stage where the convergence probability starts leveling off, and the more particles you use, the longer it takes to reach that stage. So for optimization using 10 particles, you'll get a very quick increase to about 60%, and then it'll start leveling off. If you use more particles, this takes a long time to reach that. So this is where the idea of using multiple optimizations come in. If you can run more optimizations using 10 particles to reach the same amount of fitness evaluations that you will take to use for 100 particles. And that's the basic premise of this methodology. You have a higher chance of reaching the global optimum if you use small optimizations multiple times instead of using one large optimization. So just for the probability of convergence calculation, if you have n runs, you can calculate the combined probability of convergence of n runs, which each of them have a probability of convergence of pi, and the combined probability of convergence is pc, and this is just the equation they use for that. And if you assume that each individual run has identical parameters, the rule can be rewritten in this form. Are there any questions on this? This is a standard statistical rule that we applied. So as an example, we have this theoretical graph where we take a number of independent runs and we repeat them and we calculate the combined convergence probability. So if you start off with a single run has a convergence probability of 0.1, and you repeat this twice, the this bottom curve will be the combined convergence probability if you have multiple runs, each with a convergence probability of 0.1. And you can see that the higher up the independent runs convergence probability is, the faster it will converge to almost 100% convergence probability, combined convergence probability. So you want to have an independent run that has a fairly high convergence probability, but you trade that off for fitness evaluations. So the longer you let it run, the higher your convergence probability will be, but the less function evaluations you can perform in a limited budget. So you have to trade that off. And I'll come to that efficiency in a few more slides, and I'll show you. So just to take that further, we applied this to the Hartman problem. As you can see, if you perform one long independent optimization, you see the red curve, and with 10 particles, that'll level off at about 0.35% convergence probability. And so instead of doing one long run, you do 1, 2, 3, 4, 5, 6, 7, 8, 11 independent runs, and you stop them after reaching 10,000 fitness evaluations. So you have that 0.35 convergence probability for a single run, but you repeat that run n number of times, and each time you repeat it, you see it shoot up to a higher combined convergence probability.
So you're restarting the run?
Yeah, you're restarting it, but with a different random number seed or whatever. It has a different initial configuration, but the algorithm parameters are the same. So they are independent, but they have the same convergence probability. So this was a theoretical graph that we constructed this using those two equations I showed you, and then we just wanted to make sure that this is indeed accurate. So we performed a Monte Carlo analysis. Does everybody know what a Monte Carlo analysis is? Well, out of 1,000 runs, to see what the convergence probability for 2, 3, 4, etc. number of optimizations are, you pick at random that number of optimizations in your pool, and you see how many of them converge, and you do that a high number of times, and then you use the same ratio scheme that I showed you in the first few slides to calculate your probability of convergence. But you pick any two to calculate your convergence probability for 2 runs. You pick any 2 out of that 1,000, and you repeat that, and then you take the number of that converged out of a total number that you pick those 2 out. You divide that into there, and you get your convergence probability. So as you can see, for the Monte Carlo scheme, the calculated one, the round markers, correspond pretty closely with the sampled markers. So, and we did this for all of the problems, and we saw a very close correlation. So just to come to the efficiency. So basically here you have n number of fitness evaluations. In this case, there was 200,000 fitness evaluations, and you want to get the highest possible combined convergence probability for this. So you have to decide on how many runs you want to do, and also how many runs you want to do. So from that you get the amount of runs or amount of fitness evaluations you want to assign to a single run. So the solid line, the curve over there is the convergence probability for this problem. You don't know that beforehand unless you do a large number of optimizations. So if you start out low on this curve, you can perform a lot of independent runs. As you can see, there's about 12, 13 runs using a low number where you stop your single optimization at a small number of fitness evaluations. So you can do a lot, but the flip side is if you have only 2 optimizations, you stop it halfway through your budget, you can also improve it quite substantially. So the basic idea here is that you want to for the maximum efficiency per fitness evaluation, you need to stop it at the nose of that curve. That's the optimum trade-off between number of runs and fitness evaluations. So, and this is for a budget of 200,000, and that's usually when you use one computer. If you have a parallel machine, you're going to use a different type of budgeting scheme that I'll discuss in a moment. Does anybody have any questions? Yes.
So the total number of fitness evaluation in this case is fixed.
Yeah, you're working within a budget of fitness evaluations. Say you have 2 hours of computer time on a big machine, and you want to do, you want to optimize a problem, and you know that you can only, in that time, you can only do that many fitness evaluations. Say it's a FEM analysis, you can only do a certain number of fitness evaluations in that time. So you have to decide, if you're going to optimize this problem, how are you going to decide on distributing your fitness evaluations per run. So you have to decide how many runs you're going to use. So to obtain the optimum efficiency, you have to go and decide on how many iterations per independent optimizations you need. So you have to allow enough iterations for the algorithm to converge. If you stop the run before it converges, obviously you're just wasting CPU time. If you allow too many of them, however, you get to the high point of that graph and you lose efficiency. And the amount of iterations, unfortunately, is dependent on both the problem that is being optimized and the optimizer that's being used. So we propose setting aside a fraction of the total allowed budget of fitness evaluations just to investigate how the algorithm and the optimizer, the problem and the optimizer, how they interact. So, and that fraction is that amount of exploratory fitness evaluations that you use is the NL number in this equation. So to calculate the number of optimizations that you're going to use, the capital N, you have to subtract this NL, the exploratory runs, from your total budget of fitness evaluations, and then you just divide it by the number of fitness evaluations per run. Then you get N, and this is floored. This bracket with only the bottom part is a floor, so you just round it out to the lowest integer. And then just to make sure you use up all the fitness evaluations in that budget, you just divide that into your budget again. You just subtract the exploratory from your total budget, you divide it by N. So to get that NL, the lowercase NL, you're going to use an exploratory run. So for the 3 problems, the Griewang, Hartman, and Jekyll, we optimized it with 20 particles each. And we did a fitness history plot of all of them. And then we're interested in finding the number of function evaluations that correspond to this nose. So for the Griewang problem, it'll be around 75,000 fitness evaluations. For the Hartman problem, it'll be around 10,000, and for the Jekyll, it'll be around, I guess, also 10,000. So that's when you get the maximum efficiency for this strategy. But you don't have this graph, so you can't really just go look it up. For this graph, you need to perform 1,000 optimizations, which is not always possible. So if you do a single optimization and you look at the fitness history, we observed that for all the problems that we did in the test set, the area where the fitness history starts leveling out corresponds to this area on the nose. So if you do a single exploratory run, you look at the fitness history, and you can see where the algorithm stops. It can't find any more improvement on the problem. You'll know that area is more or less the area you're interested in and going to use for NL. So we tried that for a budget of 200,000. We picked a stopping criteria for the exploratory run that corresponded to if there is no change in fitness more than 0.01 for at least 500 fitness evaluations, we stopped the exploratory optimization, and we use that number that stopped at as the limit for the independent optimizations. So for this case, for this single fitness history, it stopped at 10,000 fitness evaluations. And just to make sure that we don't have a big variation in numbers for the stopping criteria, we did that for all the problems. As you can see, there's a minimum, the maximum, and the median. And these numbers we used in the next few graphs that I'll show you. So the minimum the history that was stopped first in that pool of 1,000 optimizations is the dashed line, and the optimization that was stopped the last in that 1,000 was the solid line. So you can see for the Grierong problem, there's not a big difference. Both of them were stopped around 20,000 function evaluations. For the Hartman problem, there's a slight difference, about 10,000. This one is stopped at 5,000, or 5,000 and about 12,000. And for the Shekel problem, there was a big difference. You can see this one levels out, but then it jumps again, and you should stop it at this number.
What's in your vertical axis?
The fitness, yes. For the well, this is a set of analytical problems. So it just means if the optimum for this was 0 for the Grierong problem. For this it was minus 3.2 something. I'm not sure. So it's not really a physical quantity. It's just an analytical problem that you use to test market. We used analytical problems because we could do 1,000 optimizations. Then it's very fast when you optimize analytical problems, and you know the solution. You had to for us to construct this convergence probability graph, we had to know what the answer is beforehand. But for a real life problem, of course, you won't know that, so you can't construct that graph. So, and then we applied that budgeting method using those two stopping conditions, the two stopping points, and so the triangle dashed lines indicates when you use this strategy on the smaller number, the fitness history that was stopped early, and the circled solid line indicate the convergence probability for the stopping criteria that was last in this pool of 1,000. So you can see for all three problems there was not a big variation. If you stop it early, for most cases, if you stop it earlier, it tends to be more efficient, but there's no big degradation efficiency if you stop it on the last one. So if you use this, basically what we try to show with this is that if you use it, no matter what you get, you'll still be able to obtain a very good improvement in the combined convergence of probability. Does everybody understand this graph? Okay. So then, well, all that I explained just now was for a single processor where you have a fixed number of function evaluations that you're allowed to use. So what we wanted to see what happens if you use a parallel machine where you're not really limited by the amount of time that you want to spend on it. This is problems that people are really interested in solving. Like one of the applications that we had was a biomechanical system identification problem that we're still working on. And basically you take a set of markers on a person that move around, and you study the trajectories of those markers, and from those trajectories you can calculate what the bone geometry is. And that's a very high dimensional problem. For each marker you have 3 dimensions, and you usually end up with about 18 markers on a person. So it's also a very noisy problem where you have limitations on the camera resolution and the markers can move on the skin itself, so there's a lot of noise present in the problem. So usually what you do then is you run this problem, you optimize this problem on a parallel machine, and you let it run until you think it converged to the global optimum. So what you would like to know, however, is when you should stop it. So if you have a target confidence level, so say you want to reach 90% probability of converging to the global optimum, you can use this strategy, and it was proposed by Sneeman and Grunwald, and I have some references at the end of this slide, so you can, if you're interested, you can go look at them. And basically they proposed a rule where you have a target confidence level Q, and this confidence level is that the optimum that you obtain will be the global optimum. So in this equation, n is your total number of optimizations, and A and B is calculated by these two equations. And so A usually is picked as 1 and B is picked as 5, and these are parameters in a beta distribution. And you can go look it up in the equation, in the references. I'm not really going to go into that, but they use a standard set of parameters for A and B. And in this equation, NC is the number of optimizations that converged to the same optimum. So say if you perform 50 optimizations, and out of this 50 optimizations you have 30 that converged to the same point, then you can say that that same point has a chance of being the global optimum with this with a confidence level that is calculated with this equation. And usually what they do is, to be able to say that it goes to the same point, they define a radius in the design space, which is a Euclidean distance. So that's simply the root of the sum of squares of that, all the distances. So, and we took those same three problems, we ran them on a parallel machine, and we plotted the confidence level as a function of the fitness evaluations. So the Monte Carlo sampled points are the triangles. So that's the true, or what we think that's the experimentally defined convergence probability, and the rule that I just described, the Bayesian confidence measure, is indicated by circles. And as you can see, for all three problems, there was a pretty good correspondence. The Shekel problem didn't do so well, but it caught up to the actual convergence probability towards 200,000 function evaluations. So there's a pretty good correspondence if you want to use this rule. It's not always, as you can see on this one, it's conservative, but on the Hartman problem, it overestimated. So it's not a very good method, but it gives you some idea what your confidence measure will be if you use this on a parallel machine. Any questions on this method? So, just to conclude, this strategy yielded a pretty efficient way of improving your chances of finding the global optimum if you have a very difficult problem. It unfortunately has an algorithm and a problem-dependent parameter, that is the amount of function evaluations you have to allow each independent optimization. And this parameter dictated the efficiency of this scheme. And this method also requires your independent runs, well, your multiple runs to be independent. So you have to use a different random number seed for each run, or you have to use a scheme where you generate different positions for your swarm or your population and your GA. And this was like I described the LHS method. You can use the LHS to make sure that you have a different population each time. And if you use a power machine, this approach becomes very efficient because you can use a high number of independent runs. You're only limited by the number of processes you have. So for a very high N, if you have a lot of CPUs, you can achieve very high convergence probabilities, combined convergence probabilities. So are there any questions on this?
If you do an optimization,
Mm-hmm.
you get a solution out, how do you know what, I need to use this method, my optimization didn't work, didn't converge to the right answer?
Well, if you don't know the answer, it's very hard to tell. I mean, if you can look at the fitness history, right? If it levels out, you know that the optimizer is not going to be able to give you a better answer. But you can also stop it prematurely, like on the Shekel problem. If you look at that solid graph, if you stop it there and you think that -4 is your solution, you're obviously wrong because it can still improve. So that's when you have to do more runs. I mean, so if you do 10 of them, the chances are that you're going to see that it levels out at this point, and this is probably your global optimum. And the more you do, the more sure you are of finding this global optimum. But like I said, if you want to make sure that you allow enough fitness evaluations for the algorithm to converge. So if you see it level out at this point and you decide, okay, that's enough, but you do 10 of them, you're going to probably find one that'll jump to a better one, and you'll find an improved answer. So you know that there is a better answer. And the more optimizations you do, the more confidence, obviously, you'll have in this single, well, the run that converges to that better point. Okay. Oh, and did anybody have any big problems with the homework? Did anybody not finish it in time? I know there's some of the people that did the qualifying exam that didn't finish in time, but did anybody run into problems? I know that one thing that I had problems with was if you set the lower bound on the optimization at 0, you get singularities in the FEM calculation, and that'll make sure that you don't converge ever. So I don't know, did anybody experience anything similar or other problems?
For me, I set the lower bound at 0, and
Yeah.
it didn't converge for 1.3 G, but it converged for 100 G.
Yeah. Yeah, if you bump it up to 1 inch, the lower bound,
Okay.
it'll work fine. Did it take a long time to converge?
Yeah.
Yeah, that's the problem.
5 or 6 minutes.
5 or 6, no, that's good. I mean, but if you set it to 0, it shouldn't converge at all.
Yeah, singularity.
Yeah. So I mean, you have 0 thicknesses, so you're getting infinite stresses. Yes.
In the first problem, there are always two elements which are not fully stressed.
Mm-hmm.
So I run 400 iterations, but those two elements are still not fully stressed.
How did you stop it then? Did you just set an upper limit on the function evaluations, or? I mean, did it stop on its own, or did you force it to go longer? Yeah. Yes. But he said there's 2 elements that won't ever reach.
Well, you set the number, it's for loop, so you set the number of iterations
Okay.
to some value, you just see its asymptotes out.
Mm-hmm. What did you set it at? What did you set the upper limit as?
2 elements never reach the
Yeah. How many iterations did you allow for the FSD? 500?
I don't know.
What is the thickness
The thickness.
for the 2 elements?
I didn't check.
You didn't check? Just make sure it's not your lower bound.
Yeah, it's those elements just near the root of the beam,
Yeah.
just below the top elements and just above the bottom
Yeah, it's a free. It's a really coarse mesh. I'll look at it. Okay. If there's no other questions, we can finish. Okay.